Good morning, class. Today we want to work on the fundamental question in calculus, and that is to try to find the area under curves of specific functions. So let's consider the simplest possible curve that has this quality, and that's simply f of x equals x, or the identity function, on the unit interval. Now if we actually plot that out in a normal xy graph, we know that this is going to result in a triangle, and that triangle must have an area of 1/2, since the height of this triangle is 1/2 as well. Now the fundamental question, or fundamental approach in calculus is to divide this particular area into small rectangles like this, and then add up the area of the small rectangles. That's going to give us an approximation for the area under the curve. As the number of rectangles becomes unlimited, the approximation becomes better and better. So to do this, we want to imagine we divide the unit interval into an equal number of steps. As we imagine dividing this into n equal steps, if that's true, then this particular distance here is going to be 1 over n, and this particular position here on the x-axis is also going to be 1 over n. This is going to be 2 over n, this is going to be 3 over n, and so forth. Now, an arbitrary position here is going to be represented by k over n, where n is some fixed value, and obviously 1 can be viewed as n over n. And now to ask the question, what is the area of the rectangles? Any individual rectangle, sort of a representative one, is going to have a height that's going to be equal to k over n, and with a width 1 over n. So the representation for this in our calculus class is that the integral from 0 to 1 of f of x dx, by definition, is going to be equal to the limit, as n approaches infinity, of the summation from k is equal to 1 to n, of f of k over n times 1 over n. So this is the standard approach for every problem in calculus. Now for us, fortunately, this particular problem can be actually computed because of the simplicity of the function. We know that if we take this expression k over n and substitute it into the function, we're going to get that right back again. So the next step of this limit is going to be to compute the limit as n approaches infinity of the summation of k is equal to 1 to n. And this now is just going to become k over n times 1 over n. Now what we can do with this summation is to factor out the n, because it's not dependent upon the choice of k. So that's equal to the limit, as n approaches infinity again, of 1 over n squared, summation of k is equal to 1 to n of just k. But this particular sum is useful to us because we worked on that. We know that from elementary theory that this particular sum has a value, or representation, of n times n plus 1 over 2. So we can make that substitution, and that results into n times n plus 1 all over 2. We can now, n factorial, n squared. We can now work on this a little bit more by factoring out the 1/2 to get 1/2 times the limit as n approaches infinity. And this is going to work out to be n squared plus n all over n squared. And if we simplify this, we end up with 1/2 times the limit as n approaches infinity. This is going to divide into this. We end up with 1 plus 1 over n. And when this limit does its job, this term here is going to go to 0, and you're left with 1. And the result is 1/2. Which is exactly what we were expecting. And you may say that's a lot of work to do this particular problem, but remember that this is a general procedure and can work for anything. What allows us to do this problem is that we can work out what this sum is. We have an explicit form for this. If we were going to do f of x equal to x squared, we would still run into the same situation, but we'd end up with the summation of this for k squared, which we have a formula for, but in general, that's going to become very, very hard. And so to do the problem, we need some other approach, and that's where the fundamental theorem of calculus comes about. And in that, we'll show that to you in the next video.